hopefully iPhone coffee is starting to take effect. I can't even get my words out. I had more hopefullys, but I've just completely lost them, so I'm going to move on. So we had some really great talks this morning showing us that feedback in galaxies is really important. It's not disputed. Within our gas and star formation cycle, we have coal gas collapsing into molecular gas, turning into stars, which then explode as supernova and feed back onto the coal gas, halting star formation locally. Within this cycle, we're really talking about these two parts here. One of the best local universe examples is number 3. I push the button, M82, where you see overlaid on the optical this massive, in the red, this massive bipolar outflow in the ionized gas traced with H alpha. But there is a real problem with studying outflows in that the physics involved spans, there's a little bit of a delay. The physics involved spans from parsec scales on the scale of your supernova and your H2 regions that are launching your outflows up to kiloparsecs, where your effect of your outflows are felt over your whole galaxy, which means you really need close-by objects to study these in sufficient detail to understand them. But unfortunately, this combination of needing high resolution and things that are really big means that they're rare. But as I guess my title suggested, it's time for M82 to move over. So I'm going to take you on a little bit of a journey. This is the Virgo cluster. The background is the X-ray image and overlaid carbon monoxide maps from the Vertigo survey showing the cold star-forming gas. NGC 4383 is up here. I didn't even press that and it went then. That's great. Oh, we're going ahead. Okay. No. Yes. Wow. Best talk for technical problems. Press it once. There we go. All right, that's NGC 4383 there, take my word for it. Now, if you look at the really early imaging surveys of this galaxy, it's kind of a featureless blob. So this is a DSS image. It was originally classified as an S0 with a bit of peculiar morphology, but not really that exciting, but it's wrong. It's very exciting. Looking at more recent imaging surveys, such as Legacy, the picture starts to change. There's this very bright central region. There's a very clear dust lane through the center. And if your eye is keen, you will see some blue blobs up towards the top of the image. These are a bit more visible in the UV, which I show matched on the right there, and those star-forming knots are in the top of the image. Now this is very reminiscent of something you might call a jellyfish galaxy. This galaxy is on the infall into the Virgo cluster, but I assure you that's also not the case. When we move to the atomic hydrogen and we zoom out, oh boy, no. Where is it going? I'm not starting again. I'm not pressing, sometimes I'm not even pressing the button. So I guess using my laptop over there. You see the H1 disk is huge and also undisturbed. It's not being affected by random pressure stripping as it falls into the cluster, and as Luca mentioned earlier, this galaxy's H1 disk is about 4 times the extent of its optical size. And you can see that those bright star-forming regions agree really well with the higher density region of the H1, so they're basically just star-forming knots within the disk of the galaxy. So what we did is we went to, I even pushed the button there and I went forward, that's magic. We took MUSE pointing, so there's 3 overlaid there on the optical image as part of the MAUVE survey. And for some context in the galaxy, we've seen face-on galaxies, we've seen edge-on galaxies today. This galaxy is more or less bang in the middle, which means headaches, especially for outflows. And it's not really particularly star-bursting either. It's basically only 1 sigma above the star-forming main sequence, so that's probably one of the most normal things about it. I show on the left here just a slice of the data cube with the wavelength it's at shown by the red line on the left. But first I wanted to just give everyone an appreciation of kind of the quality of the MUSE data, because I didn't appreciate it until I started working with it. It's like Christmas. There's everyone's favorite emission line is in there. You've got H alpha, nitrogen, you've got every absorption line from stars that you want, but you've also got, helium, more nitrogen, oxygen, sulfur, even argon in there. It's just, I've had so much fun scrolling through this cube, it's crazy. But hopefully, this image, or this movie will now play. Yep, there we go. So as you scroll over the H alpha line, what you see is this massive outflow of H alpha gas, of ionized gas, that completely outshines the galaxy itself. In case you missed that, there it is again in still form. The black contours here are the optical image of the galaxy, and you see those bright star-forming knots up at the top that I pointed out earlier. in the top of the image, and then this massive H-alpha gas ionized outflow. Things get even more interesting. No, I'm not going there yet. If you do the math on this, the outflow extends more or less 5 kiloparsecs on the sky out of the plane of the galaxy. If you do an inclination correction for that, it's more like 10 kiloparsecs because of the projection effects. So this thing is huge, bigger than the galaxy itself. Things get more exciting if you pull out something like an ionized gas velocity map, which is what I'm showing here. It's just messy but fun. Again, the same black background contours, north to south or up to down on the image. You see this nice signature of rotation in the galaxy as you go from blue to red. But then the moment you go off that plane, it's just chaos, which is great fun, which is the clear signature of basically multiple velocity components along the line of sight. It appears even more so if you look at the dispersion of the H-alpha velocity. Here, where you see along the middle, you have this nice dark region with the low velocity dispersion component, and then off the plane, you have this elevation with the bright sections of multiple, basically tracing multiple line of sight velocity components along the line of sight, really clear indication of the outflowing gas. Now, I wanted to choose one science result from the analysis I've been doing with this, so I went with quantifying the metallicity in this galaxy. So what you see on the left here is a gas phase metallicity map normalized by the central value, which is about 8.6. And then darker colors are lower metallicity gas, lighter colors are higher metallicity gas. And what you see is that in the center, where this starburst is happening, you have metal enrichment, and as you go kind of up and down along the plane or the major axis of the galaxy, metallicity values typically drop off, which is what you expect for the gas reservoir of a galaxy. However, inside those cyan contours, which are what I'm using to mark the regions dominated by outflow emission, you see that it doesn't quite get as dark. The outflow basically is containing metal-enriched gas. You can quantify this with a couple radial profiles that I draw along there, where the red slit and the blue slit correspond to the red lines and the blue lines. And you see that while the red one drops off quite nicely as you go to higher radius, the blue one stays more or less constant, and it's roughly a, push the button, 0.15 dex or 30% difference in the metallicity. So the outflow is definitely carrying metal-enriched gas out into the CGM of this galaxy. That's what I wanted to leave you with today. So we discovered a new massive outflow from NGC 4383, the galaxy which extends roughly 5 kiloparsecs from the galaxy, and the gas phase metallicity is about 30% larger than what you expect for the disk. Before I go, what I've superposed here are the H-alpha map contours on a meerkat image of the continuum, which we observed earlier this year. And you can see that there is structure. It's maybe a little bit hard. If you're interested, I can show you the image later on. Just come up to me. But there's actually structure in the continuum associated with the outflow. So we're picking it up in the continuum, which is going to be some really cool science in the future. And that's all from me.